All right, here we are again after that nice long spring break. Here's what we're going to do today. We had started chapter 11 once before, and we got fairly far into it, as a matter of fact. We managed to get through our discussion about combinatorics, where we introduced several key ideas. Let's just quickly look at them one more time. This is a quick review. And so we were looking at first counting techniques. In fact, the science of combinatorics is all about counting. And so this will build us up or give us a framework for our introduction to probability theory. And so we start out with the fundamental counting principle. Oh, that's all right. It happens. Anyway. So the fundamental counting principle tells us basically how many ways there are to arrange a group of n objects. And we saw that there's a mathematical operator that will let us do this directly, which is called, let's go find it again. Jump through the examples. The mathematical operator, here it is. N factorial is the operator that we used to help us calculate the number of ways that n objects can be arranged. And of course, with arrangements, we're taking a collection of objects and we're simply changing the order. So the example we started out with was the garage, where we had 3 cars and 3 garages. And we determined that it was possible to park the cars in 6 different ways. And I listed them all here for you. And then we realized that it wasn't necessary to actually write them all out because of this wonderful factorial operator, which makes it easier because it tells us exactly how many different ways we can arrange n objects. So you might recall that factorial is defined in the following very interesting way. We started out with 0 factorial equaling 1, 1 factorial equals 1. And then it really gets interesting because then 2 factorial equals 2 times 1, which is 2. 3 factorial is 3 times 2 times 1, or 6. And then we go through the rest of the list. 4 factorial, as you can see, is 24, and we work our way up. And we do have on our calculator a factorial button, which you might recall is in the bottom left-hand corner. Let's see. Let me just get mine out. Yes, if you look in the extreme bottom, I think you can see this. Maybe you can, I don't know. It's a little tight there. I think the problem is that the focus is not good enough. It's this one right here, okay? All right, so bottom left-hand corner is your factorial operator. Oh my God, you're in an airport. Okay, well, that's understandable that the connection might be pretty awful. All right, well, I just congratulate you for getting on at all. You know how it could be in those airports, but or really anywhere. It's really surprising when you travel how poor the internet connection can be in a lot of other areas, especially once you leave the United States. You can't count on anything when it comes to the internet. It's just like, it's almost shocking how hard it is to get on the internet when you're outside of the borders of the United States. I mean, even just to go up to Canada, if you're in the water anywhere, then it's just unbelievable how bad the reception is. You think that by now that would have been taken care of, but apparently not. And if you go to further south into the Caribbean, you don't know what you're going to get. So we take it for granted, but you know, the internet is not everywhere. All right, well, anyway, so here's the how we calculate these factorials. And we saw that this is, we can use this function to calculate the number of possible arrangements of n objects, like the cars. Okay, so with the 3 cars, we had 6 arrangements, and you can calculate that very simply with your factorial operator, because 3 factorial is in fact 6, okay? 3 times 2 times 1, or 6. We also then introduced some slightly more complicated concepts, cases where we're actually choosing objects from a larger group. And in the first case, we saw what we call permutations, where we're choosing objects from a larger collection in such a way that the order makes a difference. So the example we used here was when I randomly chose 3 students to fill the 3 officers in a math club. We needed a president, a vice president, and a treasurer. And since nobody volunteered, I chose their numbers at random. And the first time I picked 3, 1, and 7, which means that student 3 is now the president, student 1 is the vice president, and student 7 is the treasurer. Had I picked the same 3 numbers, but in a different order, the outcome would have been very different, because you can see that now all of a sudden it's student number 7 who's the president, 3 is the vice president, and 1 is the treasurer. So in spite of the fact that they're the same 3 numbers, we would define these as 2 different permutations because of the fact that the order matters. So it's both the numbers that we've chosen and the order that determine each permutation. How many permutations are there? Well, here's the formula, which you can do this directly yourself with the factorial operator in the calculator. So n is the number of objects that you're choosing from, and r is the number of objects that you're choosing. And you can see how you can just plug in these numbers and come up with whatever result you need. So for the example of the math club, we had 10 students in the class, so that n would be 10. R is the number of students that need to be officers, which is 3. And so we calculated the number of ways of filling those positions as 10 factorial over 7 factorial, because that's 10 minus 3. And that, after you go through all the math, gives us 720. So there's 720 different ways to fill those positions because there are permutations. And then we introduce combinations where the order of selection does not matter. Okay, so the example we used was the toppings with the Haagen-Dazs ice cream. We were given the option to pick 2 of the 5 available toppings for ice cream. And in this case, the order of selection doesn't make any difference, because if I pick, for example, marshmallows followed by Oreos, I'll get the same result as if I pick Oreos followed by marshmallows. Either way, the toppings will just be dumped on the top, and it makes no difference whatsoever to my ice cream what order they're put on my ice cream. So therefore, each choice that I have is a combination. And it turns out that there were 10 different combinations that we could create when we have 5 objects to choose from, and we are able to pick 2 of them. So here, of course, I wrote them all down, which is easy when there's only 5 objects, but of course, at some point, it makes more sense to use the formula. So the formula this time is a little bit more complicated, not that much. I've got pizza toppings in here too, but the actual formula for combinations is, there it is. So I put these side by side so you can see the difference between the 2 formulas. It's just that extra r factorial in the denominator for combinations that separates it from the permutation formula. So now, in order to formally calculate the number of toppings that we can pick with the ice cream example, remember we had 5 toppings to choose from, so n is 5. R is the number of toppings that we get to choose, which is 2. And when you plug in all those numbers, you'll eventually end up with 10. Okay, and down here on the bottom, I've also shown how you could do that directly with the keystrokes on your calculator. And of course, you have to be careful to make sure you use parentheses whenever they are needed. In this case, the entire denominator needs parentheses because you're doing not just the factorial operators, but multiplication. So anyway, that's what we'd gotten done up to this point. And I think I remember mentioning too that example about the combination locks, which really, as we now know, are permutation locks, because each so-called combination consists of 3 numbers where the order of selection does matter. So therefore, these are actually permutations rather than combinations. So that locks are not named correctly. If you go to a hardware store and ask for a permutation lock, they'll have no idea what you're talking about. So officially, they're known as combination locks, but we know that that's not correct. All right. Now, by the way, in the other class, they asked me about the final exam date. I just want to briefly review that. We know that we started a little late this semester. Officially, our final exam week is the week of the 16th. Let's see, let me go get that. Here it is. Now, that's quite a ways in the future. That's a month from now. Well, it turns out that we've been making such excellent progress in this class that we will not have to wait till the 16th. In fact, actually, now that I think about it, our, hold on one second. I looked up the other classes schedule. Let me go see if I can get that back real fast. There, there it is. Here it is. I think for this class, since we meet at 10:30, yeah, look at that. Officially, you're supposed to have your exam on the 19th. Wow, that's way down the road, isn't it? So here's what we're going to do. Since we're going to finish early anyway, two things. Number one, no matter what date we pick, if you have a genuine conflict, you can have your exam at a different time. All right, no matter what, as long as it's a real situation, you can actually have your test done at a different time. So don't worry about that. If you've made plans, if you have plane tickets or other commitments, don't worry about it. We have flexibility here. You can have your exam at a different time if you need to. That's number one. Number two, since we're likely to finish early, I told the other class that it might be best if we get it out of the way on Monday the 9th. Okay, now, by then we should be done because we have to finish chapters 11 and 12. We have to do the problem sets, and then we have to do the sample final. By the time we're done today, we'll be at least, let's say, 3/4 of the way through chapter 11. So we're zooming along here. And so I think we can pull it off on the 9th. Now, even then, if there's anyone who would really and truly rather take it on the 19th, that can be arranged too. So there's a lot of flexibility there, but I'm thinking that our best bet is probably to do it on the 9th. And then on the 11th, the afternoon of the 11th, I'm giving the pre-calculus final at 3 o'clock in the afternoon. So if anyone can't come on the 9th, you might also want to consider the afternoon of the 11th, which I'll remind you as we go along. So there's a lot of options. Okay, well, if you like the 9th, I'm glad to hear that. I'm sure most of you will want the 9th, but just in case that doesn't work, we have a lot of other options as well. So, if you, like I said, if you've already bought plane tickets or something, don't panic. Let's say that by a horrible coincidence, you bought plane tickets on the 9th. Not a problem. We can do something else. Okay. In fact, one year, I actually had a student who had already signed a contract to appear in a movie that was going to be filmed in South Africa. And he had to get on a very specific flight or not be in the movie at all. So, he was able to take it early. Unfortunately, then the movie got canceled. So it didn't end up mattering. But I was able to, move his up because he really needed to be on that flight. So it happens. Not a problem. All right. So anyway, so what's next? We're going to start now with the second half of this chapter. The first part is our combinatorics discussion. And we learned about arrangements, combinations, and permutations. Now we're going to tie all this together and introduce the field of probability theory, which is important in its own right, but it's also important because what's coming next in chapter 12 is statistics, or at least a brief introduction to statistics, which is all entirely based on probability theory. So it's like a natural combination of two complementary subjects. And incidentally, if you find that these last two chapters are particularly exciting or interesting, the school does offer its own statistics classes, which you can take as a math elective if you still need one. Or who knows, maybe you just find this stuff so interesting that you're willing to use up one of your free electives on it. Who knows? It could happen. All right. And if so, one option that's on the table for you is statistics. Okay. It's a very different type of area because, math it can get very theoretical, but statistics is designed to be useful. Okay, ultimately, the point of statistics is to help us understand what's happening in the real world. So the focus is a little bit different, but it's still math. It's just a different kind of math. But anyway, let's look now at our probability theory discussion. First of all, what are we trying to do here? We're trying to come up with a mathematical approach to explaining or measuring or quantifying, I guess I could say, uncertainty. And of course, you know, uncertainty is everywhere. We don't know what's going to happen in the future, do we? We most certainly do not. Now, sometimes we can help ourselves, though. Like, for example, with the weather. You know, nobody really knows what the weather is going to be tomorrow, but it's gotten to the point where science can at least give us a very good idea of what could happen in the weather tomorrow. Not that they don't get it wrong sometimes, it's just that they're able to predict what could happen tomorrow based on current weather patterns and their mathematical models. And so you can rest assured that they have their own models which show, for example, the probability that tomorrow we have an inch of rain, or tomorrow we have a temperature above 70, or, you know, all kinds of possibilities. And they sit there and they churn out all these very high-powered models to help explain what might happen tomorrow. And that's where they come up with their forecasts. So what we see is, for example, oh yeah, there's a roulette wheel from the other day. So now what they do is they, you know, all those equations are reduced to this kind of thing, which is kind of nice. It's a little picture. I can see from looking at this that it's going to be cloudy today, but 54 is the highest temperature and 41. And then they look out about a week or so. They're not willing to commit beyond that because the uncertainty is just too much. But, you know, you can pretty much, I wouldn't say completely depend on that, but there's a very good chance that the weather will look very similar to that. So they're using the tools of probability theory to come up with these forecasts. Now, of course, what they're doing is very different than what we'll be doing. We're going to be looking primarily at games of chance and other types of situations which are very easy to define. The weather people's job is much harder because weather is so much more complicated, but essentially they're using probability theory to forecast the weather. I've met people, by the way, who actually majored in meteorology, and they told me it was by far the most difficult thing they'd ever attempted in their lives. It was like at such a high level that a couple of them gave it up. One or two of them stuck it out, but apparently the math involved is really crazy complicated. So, you know, I don't think anyone here was thinking about doing that anyway, but it is a very complex area. Anyway, so we're going to start out by introducing what's called a random experiment. And the random experiment simply means a process is taking place where there are outcomes. The outcomes themselves are assumed to be known in advance, but the actual outcome itself is not known in advance. So in other words, we know what might happen, but we don't know what will happen. So that, oh, I lost my roulette wheel here. Sorry, hold on. Classic example of this is the roulette wheel from Las Vegas. What happens here is that you've got a wheel and there's numbers on there. And you've got, basically the way it's structured is you've got the numbers 1 through 36, half of which are red and half of which are black. Now in Europe, European wheels tend to only have a 0. American wheels usually also have a double 0. Both of them are green. And so what happens is you have a bunch of different choices for betting. You can bet on red, you can bet on black, you can bet on odd, you can bet on even, you can bet on individual numbers, you can bet on ranges of numbers. All kinds of things are possible. But because there's 38 different numbers on here, all of which are equally likely, then any given outcome, like for example, the outcome or the 3 turning up has a probability of 1 out of 38. So when I spin the wheel, I know exactly what could happen, but I don't know what will happen. So that means this qualifies as a random experiment. Or choosing a card from a deck. We have 52 cards in the deck. Each one is equally likely to be chosen. So if I pick a card from a deck, I'm actually conducting a random experiment because I know what might happen, but I don't know what will happen. And of course, one of our favorite examples is rolling a pair of dice. Every game you ever played as a child probably involved dice. Well, maybe not necessarily. I mean, it depends on what you were playing. Board games. If you're playing video games all the time, then maybe not. But if you're playing board games like Monopoly, you certainly got your hands on a pair of dice many, many times. And you know how they work. Each die has a number on it from 1 to 6. When you roll them both, you can get anything from 2 to 12. And of course, if you get two of the same, like 2 3s or 2 6s, they're called doubles. Doubles, that's right. Remember doubles. That means you get two numbers of the same. And in Monopoly, at least, you get a new turn if you get doubles. But if you get 3 doubles in a row, you go to jail. So you have to be careful there. All right, now, what I've done here then is we're going to look at some experiments that involve dice. Now, before we go any further, I've created this spreadsheet here. What I wanted you to see is this. So it looks very colorful and complicated. I've listed all the different things that can happen when you roll a pair of dice. For example, I could get a pair of 1s, or I could get a 1 followed and a 2 rather, or a 3 and a 3, or a 5 and a 2, or a 6 and a 4. Altogether, there are 36 things that can happen when I roll a pair of dice. Now, in most games, what matters is the sum. But here we're going to think of this a little bit differently. We're not going to focus our attention on the sums like you would in the game of Monopoly. It doesn't matter what the two individual die show. What matters is the sum, because that determines where you go next in the game. But here we're focused on the evens and the odds. We want to know how many odds we got and how many evens we got when we roll the dice. So if you look at the color scheme, what this is supposed to tell us is that the yellow outcomes have an odd number followed by another odd number. And that happened in 9 different cases. If you look at all the yellows, there are 9 cases where we have an odd followed by another odd. The greenish ones are an odd followed by an even, and there are 9 of these. Okay, if you look at all the green ones, you see that there are 9 cases where we had odd followed by even. And then purple is the other way around. It's even followed by odd. And again, there are 9 of these. And finally, orange is even followed by even. And there are 9 of those. So altogether, there are 36 outcomes that can occur with a pair of dice. Each of these, by the way, is equally likely to occur. And since there are 36 possible outcomes, each one must have a probability of 1 out of 36. Okay. Now, if that's the case, that implies that the probability of odd followed by odd is 9/36 or 1/4. Oh, odd followed by even, 9 out of 36, which is a quarter. Even followed by odd is 9 out of 36, which is a quarter. And finally, even followed by even is 9 out of 36, which is also a quarter. So this is important for what we're about to do. So what I basically have demonstrated here is that if we're only focused on evens and odds rather than the individual numbers, then all 4 of these outcomes is equally likely to occur. And therefore, each one has a probability of 1/4, because the total probability of any event occurring is 1. All right. In other words, all of these have to add up to 1, because one of them must be true. When I roll a die twice, I've got to have one of these turning up. Okay. In other words, assuming the dice doesn't roll under the couch, one of these has to happen with certainty. So all of them collectively have to have a probability of 1. But because of the way we structured these each one of these 4 events has the same probability, which is 1/4. Okay. Now, of course, in Monopoly, nobody cares if they're evens or odds. You're just, like I said, looking at the sums. And in fact, maybe we won't do this now, but some other time, it turns out the highest probability here is to get a 7. Why is that? Because if you look at all these different outcomes, there's 6 different ways in which you can get a total of 7. Okay, some of the others are less likely, like 11. There's only 2 ways to get an 11. So the probability of that is quite a bit lower. And in fact, there's only 1 way to get a 12. So that's the lowest probability, along with the probability of the 2. But for our purposes here, we're only looking at evens and odds. And so that makes things a lot simpler because all 4 of these are equally likely. Okay, now we're going to represent these with letters. Okay, you've got these sets that contain the outcomes, like I have here, except here I didn't use set notation. These braces indicate that these are meant to be sets, by the way. You might recall these symbols are called braces. And these are used in set theory to indicate a set, which is simply a collection of objects, where the order, at least in some cases, the order doesn't matter. Here, the order does matter because I'm trying to indicate the first roll, and this is the second roll. So even, odd, even, odd. I've just gone through showing you why each of these has the same probability, which is 1/4. Anyway, and then going forward, by the way, we're not going to keep spelling out the words. We're going to use the letters E and O. Okay. So now what I've done here in this graph, this is a special kind of graph that you can use in cases like these. What's happening here is that when you first roll the die, you get either even or odd. And when that happens, the probability of getting even is 1/2, and the probability of getting odd is 1/2. When I roll the die twice, which we just saw, there's now 4 possible outcomes. Each one is equally likely, which implies that its probability must be 1/4 or 0.25. Now, if I continue to continue to roll the die, each time I'm doubling the number of possible outcomes. So with the third roll, I'm up to 8 now. 2 times 2 times 2 is 8. And you can see these are the possibilities ranging from all 3 evens to all 3 odds. And because there are 8 of them and they're all equally likely to occur, that implies that each one has a probability of 1/8, or the decimal equivalent of 1/8 is 0.125. Okay, and if I roll the die a 4th time, there'll be 16 possible outcomes, each with a probability of 1/16. So it just keeps going on and on and on. So every time I roll it, when I'm only focused on evens and odds, I'm doubling the number of possibilities. The graph is helpful because it's easy to overlook some of these possible outcomes when you're rolling the die many times. So this special diagram is known as a binary tree. Let me add that in here. It's not really a tree. I mean, if this was a tree, it would be upside down because the branches are going out here. But in math, we call that a tree. Binary simply indicates that on each roll of the die or each repetition of the experiment, there's only 2 possible outcomes. Binary means 2, okay? Because the prefix bi means 2. Nary just means numbers, basically. How many ways are there for something to happen? So again, you're doubling every time. And now what we're going to do here is gather up all the possible outcomes of our experiment into a very special kind of set, which is known as the sample space. And you notice again, I'm using the braces, and here's all the possibilities. E, O, E, and O. Remember, just E simply means even, O means odd. And so those are my 4 possible outcomes. They're all gathered together in this special set. And I can use this set to help define probabilities for any particular outcomes that I'm interested in. Okay, now, having said all that, we're going to need to take a bit of a detour into an area that you've seen before, but maybe not for a while. And that area is called set theory. And you might remember that we can perform algebra on sets, okay? But we are using operators that are very different than what we're used to seeing. In other words, instead of using multiplication and addition and that type of thing, we have a different set of operators that we can apply to sets. So we have to review this a little bit because, like I said, it may have been a while since you saw this before. But you've seen it, I can guarantee you. There's no way you got to this point without having seen this before. You know, it's like you learned it probably around the same time you learned about Roman numerals, you know, it was that long ago. All right, so let's start here. Oops. So here's my sets. These are I've got A, which contains 1, 2, and 3. B contains 2, 3, and 4. C contains just the element 5. And D contains the elements 1 and 2. So this operator over here, see that big U here? That symbol stands for union. And it doesn't mean like a labor union. It means that you are going to take 2 sets and simply combine them. So in other words, A union B is the set that contains all the elements that are in A or B or possibly both. So I've literally just taken A and B and combined them into a big new set, which we'll call A union B. Now, in some books, instead of using the symbol union, they use the English word or because it means the same thing. Again, the union contains all the elements that are in either an A or B or possibly both, if there are any. And in this case, they do both have a 3. If you notice, though, we don't list the 3 twice. This is only meant to indicate how many unique elements there are. We don't need to list it twice. It's just 1, 2, 3, and 4. Is it starting to ring a bell? Does this look familiar? Is it starting to come back and you're saying, wait a minute, I remember doing this? Yes, it was fun, wasn't it? Yes, but it's been a while, hasn't it? This is probably, it wasn't even high school. It was probably even earlier than that. But I don't know for sure. Every school is different. But it's possible that it's been several years since you saw this, but you definitely did learn this. Now, there's another operator that we need to know, and it's called intersection. That upside down U is pronounced intersection. It is equivalent to the English word and because when you apply an intersection to 2 sets, you're looking for all the elements they have in common. So in other words, I want to know what are all the elements that are in both A and B. And in this case, it happens to be just the 2. That's the only element they have in common. So therefore, the intersection is the set containing 2. Okay, so, and again, it's equivalent to the English word and, which some textbooks use instead of the symbols. Okay, so far so good. I hope these are all fun memories. Yeah, some branches of math are actually kind of fun, aren't they? Yes, this is definitely one of them. That's right. Or at least fun by math standards. The word fun is such a relative word, isn't it? It sure is. But anyway, so now here's an interesting, this one is a little more interesting because look what can happen. What if I took 2 sets that have nothing in common with each other, like A and C? Well, then my intersection is defined to be the so-called empty set. Yes, if you're breaking up, yes. Yeah, unfortunately, some people in the class are having trouble with their internet connection. But don't worry, not just these slides from 11 themselves, but what we're doing today, the parts that I'm adding by hand will be there as well. Okay, so it'll say chapter 11 with notes from 418:22. So you won't miss any of this. Yeah, technology, I'm telling you. You'd think that by now the internet would be like easy everywhere, but you can never assume the internet will work no matter where you are. Where I live, this phone, this wonderful little phone here, there's a dead zone right around my building here where if you want to make a phone call or get on the net, it's just not going to happen. It's just there's certain, I don't know, it's the trees or the hills or whatever the problem is. It just doesn't work. So you have to walk around and find a spot where it actually starts to work again. Okay. I mean, you think by now. All right, well, anyway. So in this case, A intersects C is defined as the empty set. If you notice, we can define that in two different ways. We've got the braces with no elements. This zero with a slash through it is often used as well to represent the empty set. And, you know, it does happen. Not every set has elements in common. And so their intersection is empty. And when that happens, we say that A and C are mutually exclusive. You may have heard that term before, mutually exclusive. There's no elements in common between them. You know, it would be like the set of odd numbers and the set of even numbers would be mutually exclusive because there can't be any overlapping between them. All right. So that would be a perfect example of what it means for two sets to be mutually exclusive. All right. Now, what else? What other key concepts do we need to remember from set theory? We have this notion, and by the way, it's hard to draw this properly. This thing I've got here under the line, it looks like a C, but it's meant to be like a U kind of thing, like a sideways U. And that is the symbol for subset. And a subset means that one set is completely contained within another. So here, for example, D is a subset of A because all the elements in D are also in A. Okay, D has 1 and 2, A has 1, 2, and 3. That means that D is a subset of A. Okay. Now, you can think of a lot of examples in the real world. For example, all the students in this class are a subset of the entire student body at SUNY Purchase. Okay, because everyone in the class is also a SUNY Purchase student. Or I guess you could think of the odd numbers are a subset of the real numbers because they're all reals, but there are others as well. Now, oh, I made this one up. Art majors at SUNY Purchase are a subset of all the students at the school. Okay. Now, what about this case? What about C and D? Well, you can see that C is not a subset of D because 5 is not in set D. And so the symbol for that is just the subset symbol with a big slash through it. And that simply means that C is not a subset of D. You know, it's kind of like, you know, it's gotten to be the trend these days. Like if instead of having a sign that says no smoking, what they do is they have like a circle around a cigarette and a big slash through it. And that's meant to indicate, no, don't smoke. Okay. It doesn't say the words no smoking anymore. It has the cigarette with a big red circle and then the slash. It's the same thing. The slash means the opposite. It's like, you know, in the 19th century, what's interesting is if you ever noticed, like a lot of different professions have like a sign that is associated with them. Let me just show you a picture of what I'm talking about here. So like this, for example, this symbol means that there's a doctor in this office. Okay, so if you were walking down the street and you see this symbol, that means that this is a doctor's office. And so apparently what was common in the 19th century was that relatively well-off people, let's say you live in Boston or New York or whatever, and you're fairly wealthy and you're not going to actually do your own shopping, that's for sure. You're going to send your servants out to do whatever needs to be done. Servants almost certainly were illiterate at that point in time. And so how would they know what stores to go to? Well, they would see the pictures and they would say, oh, wait a minute, I need to fill a prescription for my my boss. Oh, that right there tells me this is a pharmacy. Therefore, I go inside and get the prescription filled. That's how it was done. So the symbols are now coming back, if you notice, like, and then they went to all words. Oh, is that right? The tattoo, there's an actual tattoo to indicate that they have, wow.
Yeah, one of my friends from like high school got a tattoo with like I think it was like insulin, some type of insulin that they take underneath it to show if they were to ever like pass out that they have diabetes in case they didn't have their tag.
Wow, I like that. I didn't know about that. Yeah, because that way, like you can lose the tag or the bracelet, whatever it is, but you can't lose a tattoo. That's very interesting. I wasn't aware of that. Thanks
Shit,
for
it is
bringing
real
that
hard to
up.
lose a tattoo.
Yes, it is. Yeah. And so the symbol tells the medical people that you should not be given certain drugs because you have certain medical issues. That's very interesting. I like that. But yeah, so these came to be symbolized with that particular type of profession. And so that's how even people who couldn't read would know, oh, this is a pharmacy. So that's what made me think of the cigarette sign with the big circle through it and the slash. Even if you don't speak English, like say let's say you're in the United States and the sign says no smoking, but you don't speak English, that's not going to help you very much. But the circle with the slash through it is like a universal symbol of don't do whatever it says in this picture. And if that picture is a cigarette, then you know that it means don't smoke here or don't cross the street here or whatever the case may be. Oh, they used to have that. Now, you know what, they've gotten away from that now with walking. They have the little walking man and then they have the big hand when you're not supposed to walk. I guess they figure that's more universally understandable than a big circle or with a slash, but whatever works. But of course, now with our iPhones, with all the technology, every single item on this iPhone is an icon of some kind. There's no actual English instructions anymore. You're using a website and you need to do something. It's up to you to figure out what the little icons mean, which is kind of unfortunate, in my opinion. Sometimes the English would help, but they don't seem to want to do that. Not even like a little helpful hint, like if you hover over it, shouldn't there be hints? No, they don't like it that. I mean, all these high-tech apps and all this good stuff, it's all pictures. There's never any actual words anymore. I'm not so sure if I like that. If I can't find something, the pictures aren't going to help me if I don't know what the pictures mean, though. That's where the problem is. It's understood. If I didn't know that this meant pharmacy, this picture doesn't do me any good either. So it's a bit of a quandary, I think. But anyway, let's get back to this. The slash just means do the opposite. It always has in math, by the way. That slash has always indicated the opposite of what that symbol means. So anyway, we're going to define a very important concept now, the event. For the most part, we'll be calculating the probabilities of events. And an event, and here's why we needed to review set theory, is a subset of the sample space. So when I'm rolling the die twice, for example, what if I am playing some kind of a game where my prize depends on my not getting two even numbers? And so F is the event that I get at most one even number, which basically could be rewritten as only 1 or 0 evens. That contains the elements EO, OE, and OO. And you can see F is clearly a subset of S because every element in F is also an S. And so therefore F qualifies as what we will call an event. And we can now calculate the probability of this happening based on the way the experiment has been structured. And when I say that, what I mean is our knowledge that each of these 4 outcomes is equally likely. And then we'll see what happens when that's not the case. Okay, all right, well, anyway, let's see how this would work. So what you can do is just say, well, listen, all I have to do is calculate the probability of each of these elements individually and then add them up, and that will always work. And so we've already seen that each one of these has a probability of 1/4. So therefore, the total probability of F is just 3/4 or 0.75. So it's pretty straightforward. Just add them up. Wow, that was easy. But in this special case, when each element is equally likely to occur, there's a way we can even speed this up further. But remember, this only happens when we have all equally likely outcomes. And that means that we're just going to say, listen, we can just take the number of elements in our event and divide by the number of elements in the sample space. But again, this only works when all the outcomes are equally likely, like they were here. Remember our little spreadsheet, we proved that these are all equally likely. So therefore, all I have to do is say, well, listen, F contains 3 elements and S contains 4. Well, there you go. It's just 3/4 or 0.75. So then in that case, this is even simpler. All right, now here's another one. Now this time we're going to roll the die 3 times just to get some practice. And that means, of course, as you know from the diagram we had earlier, there's 8 possible outcomes. Let me just go get the diagram back. There you go, there's 8. Now, what I've done here is I've organized them, though, in a specific way. You'll see why in a second. So if we roll the die 3 times, I've gathered up all 8 outcomes, but I've done them in a very particular order. I've organized them so I start with the cases where there are 3 evens, which is just the one way. Then I have all the cases with 2 evens. And then I have the case with all the cases with 1 even. And then finally, I have the only case where there's no evens. So they're all 8 of them are accounted for. By doing it this way, it makes it easier to identify the ones that belong to a particular event. You don't have to do it this way, but I think it's a good idea. Okay, otherwise it's easy to overlook events that belong in your set. So let's say that in this game, I'm rolling the die 3 times and I only get a prize if I get at least 2 evens. At least 2, of course, in this case means 2 or 3. And so because of the way I've written this sample space, it should be clear that A represents all the elements in this top row, where I've got either 3 or 2 evens. And I've written it down here. This contains EE, EEO, EOE, and OEE. Well, again, based on what we've just gotten through doing, because there's 4 elements in that set, and there's 8 in the sample space, and they're all equally likely, that implies that my probability is 4 out of 8, or a half. Oh no. All right, well, I'll tell you what. Yeah, that isn't helping matters. I'll go ahead and carry on, and then when you get back, let me know, and we'll quickly review what you missed. But remember, this is being recorded, so if worst comes to worst, you can watch. But that's really annoying. Why do they have to do it now? All right. So let's make a note. This is where everyone had to leave the building. Now, I know from experience, those things are never quick. You're probably going to miss at least 5-10 minutes. So, oh my God, this is so frustrating. especially because this is the example I really wanted everyone to see, where what happens when these are not all equally likely. Well, you know what? Let's do this. Just because everyone in WABAC has to go outside for now, why don't we maybe have a 5-minute break? And then we'll come back, we'll go slowly so they don't miss too much, okay? Because I really want everyone to see this example. All right, I'll tell you what, let's knock it off for about, let's say 5 minutes, just to give them time to get back. And then we'll carry on from there, okay? Good, all right. I have, yeah, no problems there. All right, so let's do that, and then we'll carry on from here. All right, is that fire alarm over? All right, well, we'll start slowly. How about that? Okay, so here's what's happening. Now, I wanted to show you another example where we're rolling the die twice, but each outcome is not equally likely, and see how that works differently. So this time we have to imagine that we're using a couple of very strange dice. Um, Instead of having the normal numbers from 1 through 6, they have numbers 1, 2, 3, 4, 5, and 7. Who knows why, but they do. And so that means that each roll there's only 2 possible evens and 4 odds. So now all of a sudden, instead of evens and odds each having a probability of 1/2, the probability of getting an even is 2 out of 6, which is a third. And the probability of getting an odd is 4 out of 6, which is 2/3. Well, that does change everything, doesn't it? So while the sample space hasn't changed, the probabilities themselves have changed. So let's take a look at how they would be calculated. So already we know that each roll has a 1/3 chance of being even and a 2/3 chance of being odd. So that means EE, all of a sudden, instead of having a probability of a quarter, what's happening here is you're multiplying the probability of even by itself, and you end up with a probability of 2 evens of 1/9. For EO, you're multiplying the probability of an even by an odd, which is now 2/9. OE is the same. It's 2/3 times 1/3, which is 2/9. And then finally, OO, you're multiplying 2/3 by 2/3, and you're coming up with a probability of 4/9. Now, here's an important detail. If you notice that just like all the other cases, no matter what the individual probabilities are, it must be true that these 4, regardless of what the individual values are, absolutely have to add up to 1. Okay, so if they don't, that means you've done something wrong. All right, then. So they do add up to 1, as you can see. And now we can go ahead and calculate the probability of F under these circumstances. Okay, so in other words, with this very strange pair of dice, the probability of getting at most 1 evens, we can't use this formula we had before. In other words, we can't just say it's 3/4. Even though there are 3 outcomes in F and 4 in S, it doesn't matter because they're not equally likely. So here's what we'll do instead. We'll calculate each individual probability and add them up. Okay, and so that approach always works. Okay, so I've got 2/9 plus 2/9 plus 4/9 adds up to 8/9. And that's the new probability of F, given the strange dice that we're using. And in principle, we could have any number of faces on these dice that we want. In fact, you might be surprised to discover that not all dice even have 6 sides. It's possible to have more. In fact, I went out and found some more this morning with my other class. Look at this one. This die has 16 sides. What is, oh, I'm sorry, don't understand what that means, D20.
Oh, there's a dice with like 20 different sides.
Oh, there
that's
is,
used for
yeah.
D&D.
Oh my God, this one is 16, it looks like. It's for, yeah, Dungeons and Dragons apparently requires dice. I've never played it, by the way, that have more than the traditional 6 sides. And apparently it's not a problem for the manufacturers. It's just that it's a little unusual. And in fact, well, let's see, wow, those are so cool looking, aren't they? I might want to play just to get my hands on these dice. Look at these guys. They're so cool. Wow. But anyway, so but I think I lost the page here, but you can actually find, believe it or not, 100 sides. Oh my God, how is this even possible? But it exists. They do. Oh, look at that. Amazon has it. 100 sides. Why would you need 100? I don't know. I can't imagine a game that would need 100 sides, but it does exist. They do have them. in principle, you could have anything you want when you think about it. How about a picture of an 8-sided die? Yeah, it's a little weird. Look at some of these. This one is 60. Well, I guess in principle, any even number, obviously, if you're going to try 7, it's not going to work. Physics will prevent that from happening, but oh, look at these. Wow. So many different ones to choose from. Look at these guys. Wow. As opposed to the standard Monopoly dice that everybody grew up with. Yep, there they go. But anyway, so far, I think these are the winners for the coolness competition for today. All right, but anyway, so yes, so these dice here, they still had the 6 sides, but not the right number of evens and odds, the same number. In principle, they can have anything, but the standard ones, of course, have 1 through 6 on either side. If you go to a casino, they're going to have 6 sides. Let's put it that way. All right. Well, anyway, but they have different colors and stuff too. I just remember some of the games had red dice in them. I don't remember which ones anymore, but they did have red, but they were still the traditional 6-sided dice. But anyway, now that we've done this part, we're ready to look at the so-called rules of probability. Now, the rules of probability are designed to help us with more complicated situations. So you can see that there's 3 of them. The first 2 are pretty straightforward. The third one, the multiplication rule, is going to take a little bit more explanation. But the first 2 at least involve only concepts that we've seen so far. So they're not too, I mean, they're a little involved, but they're not that complicated. The addition rule, which is meant for cases when we're taking the union of events. The complement rule means we're looking at complements, which we'll have to explain when we get there. And the multiplication rule is meant for intersections. All right. So let's take a look at this addition rule. By the way, are those people back from the fire alarm? Wow, this is frustrating. All right. The addition rule, you can see it's right there, and it is based on what we were doing earlier. We have the probability of a union of events A and B equals the probability of the 2 individual events minus their intersection, the probability of their intersection. Now I'm going to show you in a minute a graph that helps us visualize what this is all about. And when you see this, you're going to say, wow, it's been a long time since I thought about this type of graph. But you've definitely all seen it before. All right. So I'll give you a minute to catch up, and then I'm going to show you a graph which will make you think, oh, wow, I remember this, but it's been a long time. All right, are we ready? Let's take a look. The Venn diagram, that's right. Remember your old friend, the Venn diagram? It is a perfect tool for illustrating the relationship between sets. So here I've got sets A and B, and they overlap. And where they overlap, that is where we have their intersection. You'll see why I have Roman numerals there in a second, but we have A and B, and they overlap in region 2, where they have the intersection A intersect B. The box, by the way, represents the sample space. Everything in there is in the sample space. Outside are the elements that are not in the sample space, and they are now irrelevant. Okay, so what are we going to do with this? How is this going to help us with the addition rule? Well, this will help us understand how the addition rule works. All right, so for example, draw it again here. You can see now the union of A and B consists of areas 1, 2, and 3. A by itself is areas 1 and 2. B by itself is 2 and 3. The intersection between the two is number 2. So if I add up A and B and subtract, well, actually, if I add 1 and 2 plus 2 and 3 minus 2, you can see that it reduces to 1 plus 2 plus 3. So in other words, the reason why we subtract that intersection is because if we don't, we would be including section 2 twice. We don't want that. So instead, we subtract it right here. Actually, let me neaten this up a little bit. So this is the logic behind subtracting the intersection. We don't want to count the intersection twice. All right, now we're going to go back to our die rolling experiment, and we're going to assume that we're back to the normal dice that have 6 sides on them, which means that even and odd are equally likely. All right, so let's do that. So our sample space consists of EE, EO, OE, and OO. Now, again, each one is equally likely. And let A be the event that the first roll is even, which means it consists of the points or the sample, events EE and EO. And then B is the event that there's exactly one odd roll, which means it includes the elements EO and OE. And as you can see, I circled the ones that they have in common. They both contain EO. Now, we're going to ask the following question. What's the probability that we get either the first roll is even or exactly one roll is odd? And that means we're using a union, which means we're also going to use the addition roll. All right, so that means that's your signal that we're going to use the addition roll. Okay, the or is equivalent to union. Okay, so what we have to do is figure out the individual probabilities and then plug them into this addition rule formula. So let's go back and revisit these. A, remember, is first roll is even. The second one represented exactly one roll. Is odd. And if you notice, because the sample space elements are all equally likely again, the probability of A can be easily determined to be 2 out of 4, which is a half. And for B, based on the same logic, the probability of B is 2 out of 4 again, which is a half. Now, the intersection is the only element that they have in common, EO. And because there's only one element in the set, that means that the probability of A intersect B is 1/4. So we've got all 3 of our probabilities. All that remains to do is plug them in to the addition rule. All right, so I'll give you a minute to catch up and then I'll show you the results. All right, here we go. So you literally just plug everything in and you can see that you end up with 3/4. And it's really that straightforward. All right. That's all you had to do. Now, by the way, in this case, there's another way we could have gone about this. And again, we're taking advantage of the fact that the elements in our sample space are equally likely. Okay, so that means we can speed this up just a little bit by doing the following. We can go back to the beginning and say, well, listen, given the elements that are in A and B, all I have to do is write out what elements belong to the union and then count them. And since there's 3 equally likely outcomes in the set A union B, and the sample space has 4 equally likely outcomes, that means that my probability, again, must be 3/4. But just remember that what we just did here only works because the elements in the sample space are all equally likely. Okay, there's usually more than one way of getting to any result in math. Now, what about the case when the two events A and B are mutually exclusive? What happens then? Let's find out. Now, this is an important detail. The probability when 2 events are mutually exclusive like this, if they are, suppose that A and B are mutually exclusive for some reason. We know that their intersection is the empty set. But it turns out that this implies that the probability of that intersection is 0. And we think of this as the impossible event. Okay, it's like, imagine if I told you that I'm going to pick a random number and I want to know the probability that it's both even and odd. Well, clearly that's not going to happen. There's no numbers that are both even and odd, and therefore the probability of that happening is 0. We call that an impossible event. Well, if that's the case, and by the way, just as a follow-up to that, the probability of the entire sample space is defined to equal 1. So these are 2 important results that you need to know. The probability of the sample space is 1, and this is known as a certain event. Whereas the probability of any set that is the empty set is 0. We call that an impossible event. Oh, it's right there already. What am I doing? Okay, whatever. So if A and B are mutually exclusive, their intersection is empty, and therefore their probability is 0. So therefore, when that happens, we can streamline the addition rule because there's no point in subtracting that intersection. So here's what I mean. Wait a minute. The full rule is up here on top. But if A and B are mutually exclusive, the probability of that intersection is just 0. So I can simplify this by writing it as the probability of A union B equals the probability of A plus the probability of B. And from now on, we're going to call that the simplified addition rule. But just remember, we can only do this when we know for a fact that A and B are mutually exclusive. It's just a little bit quicker, that's all. We see that they're mutually exclusive, well, then we can just add them up. And actually, let me throw in here a new Venn diagram so you can see why this is happening. So the probability of their union that's it. And that's all there is to it. There's no overlapping, there's nothing to subtract. You just add them up. All right. So let's do an example. With the die rolling experiment, the same case, the same sample space, the same everything. This time, though, we're going to have two very interesting events defined. A will be the event that the first roll is even, and B will be the event that the first roll is odd. Now, clearly, those are mutually exclusive events, but we're going to prove it by writing out all the elements that belong to both of those events. Okay. So we have for A, let me just, oh, there it is. It's up there. A would be EE and EO, B would be OE and OO, and you can see they do not overlap. They can't. So therefore, the probability of their intersection is 0. But individually, A has a probability of 2/4 or a half, and B is 2/4 or a half. So here's the big question. What's the probability that the first roll is even or the first roll is odd? Oh, okay. Well, it sounds to me like a job for the simplified addition rule. Okay, so in other words, the probability that the first roll is even or odd is the probability of A union B with the simplified addition rule. And by the way, again, this is one of those cases where it should be pretty clear this is going to be 1 because the roll has to either be even or odd. It can't be anything else. So, but we want to prove it with the addition rule. But we know in advance that the probability has to be 1 because one of those things has to be true with certainty. All right, so let's jump ahead and start throwing in some numbers. And again, I mentioned here that the probability of 1 means we have a certain event. A means EE and EO, which means its probability is a half. B is OE and OO, which means its probability is a half. And we add them up and we're all set. That union has a probability of 1 because, in fact, let me put this in here. We already know this. Just as a quick reminder, the union of A and B we put these together, EE, EO, OE, and OO. This is just the sample space. And by definition, the sample space has a probability of 1. So therefore, the final result has to be 1. All right. So that was the addition rule. Now we're only going to have time to briefly consider the complement rule. I just want to introduce some very key concepts before we knock it off for today. This is about as far as I got with the other class. I don't want to push it. There's no hurry here because we're already ahead of schedule, but I want you to see what complements actually are. Now, by the way, the word complement can mean a lot of different things. It has a very specific meaning in math, though. Two events are said to be complements formally if two conditions are true. Number one, if their union gives us back the entire sample space, and number two, if they are mutually exclusive, then we conclude that A and B are complements. So I've got several examples here to make it clearer what this actually means in practice. Okay, so that's the formal definition. I want you to see is, or give you an intuition as to how this actually works. So, what if we pick a card from a deck? That's our experiment. A will represent the event that the card is red, and B will be the event that the card is black. And also, I noted here, the entire deck is the sample space. So the question becomes, are A and B complements? So we have to think about whether or not they satisfy those two requirements. I'll tell you up front, the answer is going to be yes, but let's just see why. All right, so remember what it means. In fact, I'll tell you what, just to make it easier, I'm going to copy this. Just a quick reminder what it means for two events to be complements. So, first of all, is the first condition true? Is there a union the entire sample space? In this case, that means is the union of the red and the black cards equal to the entire deck? And the answer is yes. On the other hand, is it true that no cards are both red and black? And the answer is again, yes. So you know what that means? They must be complements because both of the conditions are satisfied. So let's do that down here. So A union B equals S means the union of the red and the black cards is the entire deck. And no cards are both red and black. Therefore, A and B are complements. Oh, you know what I forgot to do here? Hold on. Forgot to put in the conclusion. Let me just do this real fast so there's no confusion. And I'll come back to that in a second. Hold on, it's saving. One of the negative things about all this wonderful handwriting on the slides is that they do suck up a lot of memory. But all right, so anyway, what this is telling us is that A and B are indeed complements of each other. So again, the way to think about it is that between the two of them, their union gives us back the entire sample space, but they don't overlap, okay? That's what we're after. Now, how about this one? Our sample space is the natural numbers, which you recall from way back in the beginning is 1, 2, 3, 4, et cetera, et cetera. If A represents the even numbers and B represents the odd numbers, are these two events complements? Well, based on the same logic, the answer will prove to be yes. Because their union, the union of A and B, is the entire sample space of natural numbers, but they don't overlap. Okay, so that tells me right away they must be complements. All right, so let's look at the next slide and see the proof. Yeah, A union B is S, all natural numbers are either odd or even, but none of them are both. Well, that would be strange. Imagine a number that could be both. Well, theoretically, if you're looking at the whole number, 0 can be thought of as both even and odd, but we won't deal with that here. We'll focus our attention on the natural numbers, and therefore all the numbers are either one or the other. Excellent. So another example is the white and the black pieces on a chessboard. Same thinking. All the pieces have to be either white or black, but none of them can be both. That's why they're complements. Now, I'm about to show you an example of two events that are not complements. I want you to see what happens in that case. So now, instead of having white and black pieces on a chessboard or odd and even numbers or red and black cards, what's happening here is that I'm taking a standard deck, which, in case you've forgotten, there's 26 red and 26 black cards. Among the red, there are 13 hearts and 13 diamonds. And among the black cards, there are 13 clubs and 13 spades. Now, what if I pick a card from the deck and define the following events? A means the card is a heart. B means the card is a diamond. Are they complements? Well, one of the conditions we need is true in the sense that A and B can't have no elements in common. In other words, no card can be both a heart and a diamond. So the intersection of those two is indeed empty. Where's the problem though? Oh, well, the intersection is empty, but is the union equal to the entire sample space? And the answer is no, because their union only equals, let's add that here. A little further explanation here, that it includes only the red cards. We still left out the spades and the clubs. That means that the answer is no. These are not complements. Because one condition was true, but the other was not. And so in other words, it has to be both of them. It's not enough for one of these to be true. It has to be both. So in this case, A and B are not complements. And that just means that we can't apply the complement rule to them. That's all. Now, one more detail I want to show you. Notation wise, what you see sometimes is when two events are indeed complements, let's say A complement will be written with a C, which means complements. In other words, when you see A, C, it means the complement of A. And so finally, I'm going to show you the complement rule. It's written in two equivalent ways. We're not going to have time to go through it right now. We'll pick it up on Thursday. But this is what this rule is all about. And by the way, we're going to prove it too when we see it on Thursday, using all the rules we've seen so far. So you can write it in one of two equivalent ways. Probability of A equals 1 minus the probability of its own complement, or the probability of A complement equals 1 minus the probability of A. They both tell me the same thing. All right. So, by the way, did everyone get back from the fire alarm? Wow. So there it is. Now, as soon as it's ready, I'll be posting this video on Moodle. Not Moodle, sorry. It has to go into my YouTube account. Moodle doesn't have enough memory, apparently, to store videos, which I spoke to them about this during the COVID, and they said, well, you know, Moodle's a great system, but it doesn't have that much memory or whatever they told me. It was some technical reason. So it'll be on my YouTube account, just like we have a couple of others. And there's a special playlist just for our videos, because if I didn't have playlists, you'd have to sort through a lot of videos that I've made over the last couple of years. So you shouldn't have any trouble finding it, but it does have to be processed into MP4 format. So it won't be ready immediately, but it'll be ready later on today. And then you can go through it and review everything we did. And then I'm pretty confident I'll be ready to come back on Thursday. I was in much, actually, I can tell because I was in much worse shape in my 8:30 class. I was sneezing and coughing all over the place, and now I seem to be calming down a little. That's a good sign, I think. But so I'll be there on Thursday with the exams, which, by the way, if I didn't mention it before, I created a grade book in Moodle so that you can see your scores from the second midterm. I also created one for the first midterm just for completeness sake, but you should already have received your exam anyway. But this way, you don't have to wait till Thursday to find out how you did. Okay, I didn't want to tax your patience. Since I finished them, God, it was almost immediately after I gave them to you. So they've been in my car all this time. And I just want to make sure you don't have to wait any longer to see them. So anyway, if there's no last minute questions, I guess we'll stop right here. And don't forget about those cool blue dice that we saw. If you're really dying to have a 16-sided die, They are out there somewhere. Look at those. How cool is that? Wow.
They actually sell whole sets of D&D dice, like whole
Wow.
sets that match each other. I got one of my exes, like a cube pair for Christmas or something like that. And
Man.
no, they're actually really cool. Maybe you should try D&D. I think you'd like it.
Really? Okay. Well, I'll look into that because I've heard of it, but I've never actually attempted it. Um, you know
I
why?
was I'm not crazy into it myself. I've
Oh,
really
okay.
only played it once or twice, but I have a lot of friends of mine who really love it.
Oh, okay. Yeah. No, I'll look into it. That's for sure. Especially if I get a chance to roll these cool dice. I'm definitely there. That would be enough reason alone to play as far as I'm concerned.
It's the best part of the game is all the pretty
It,
dice.
the dice. Yeah, I like that. So, oh, I see an 18 up there. This can't be a 16. This must be a 20-sided dice.
It must be a D20.
Oh, okay. Now I get it. Okay. All right. Well, anyway, I guess so I guess I'll just see everyone on Thursday then. All right. Have a nice day.
Bye, Professor. Thank you.
All right. Bye.